Greetings, Astronomy 10, and welcome back to theoretical astrophysics, nuclear physics, quantum mechanics, and all of the fun parts of astronomy. Don't worry, just like last time, we're not going to get too deep into the fundamental mechanics that make up these branches of physics. We're only going to explore just enough that we get a pretty decent understanding of what's going on in the astronomy context, just as promised from the beginning of the semester. The outer layers of the sun are not like the inner layers of the sun. We have an atmosphere where it's really kind of diffuse, even though parts of it, especially the individual particles, can be quite hot. We're still talking, possibly in the millions of degrees, some of them. But the sun is made of gas, right? Hydrogen and helium gas. And so if you weren't going to get instantly vaporized by the incredible amount of temperature in the atmosphere and the body of the sun, if you weren't going to get vaporized and you were to fall all the way through it, because it's made out of gas, it would seem sort of like falling into one of the gas giant planets. Of course, it's going to get dense enough that eventually it's too thick to see. Goodness. Like falling deeper and deeper into dense fog, eventually it would become kind of like liquid and then really dense, like solid. But for the sun, it becomes much more dense because there's so much more matter in the sun that eventually it would become so thick it would just be like, not like a liquid in the sense that we think, it'd be much more dense, especially when you get down to the core. It's beyond solid, right? It's so dense that even though it's a gas, it's just hydrogen and helium, it's very, very dense. Now, last time we talked a little bit about energy being generated and how it gets to the surface. And the reason that we know any of this, of course, about the sun is that we sent probes to the sun going as far back as like the 1960s. And so we're able to figure out the temperatures of various regions of the sun and how that relates to our model. And of course, it works pretty well. And we can kind of figure out the luminosity, or from the luminosity we can figure out what the density of the material is at various depths of the sun. And if you look at, I think it's maybe the second or the third image in today's image bank, there's an outer layer, the very, very outermost layer of the surface of the sun is this thing we call the photosphere. Below the photosphere is where light bounces around between atoms, getting absorbed and reabsorbed and reemitted and reabsorbed ad nauseum for something like 100 years before the light finally escapes the surface and travels out through the universe at large. When it finally gets there to this layer that's maybe about 5, let me just put it here in the photosphere. This is maybe about 500 kilometers thick or so. Essentially because this layer is the last layer where light gets reabsorbed and re-emitted the last time. This entire region generates light. This entire 600 kilometer deep region generates light out into the universe. Of course, we know that a little bit from our measurements and calculations for the density of the solar material at those depths. In any case, if you look at the sun, if you look at it kind of straight on, it appears brighter in the middle. And if you look at it sort of at the edge, it looks dimmer. Oh. Yeah, okay, so the photosphere is the very outermost layer of the sun. And if you look at like the middle of the sun, it looks really bright. And then if you look out here kind of at the edge, it doesn't look as bright. And the reason for that, of course, if you're looking at just, this sliver of edge out here, you're actually looking at less material, right? There isn't more behind it or whatever, not like there is if you look at here in the middle, there's, the entire star that you would have to look through, right? We call this effect, when you look at like the edge and it not being as bright compared to the center, we call that limb darkening, just like it sounds. Limb, like your arm or leg or whatever, darkening. And while I know what this sounds like if you drive around in your car with one arm out the window the whole summer or whatever, then one of your arms is all like tanned compared to the other one. You get a nice farmer's tan, but only on one arm, right? Limb darkening. I know it sounds like that, but what it means is black body radiators like stars appear dimmer around the edges as compared to looking directly in the middle, because you're actually looking at less light generating material. The temperature of the photosphere is something like 6,600 Kelvin, which is like 6,300 degrees C, something like that. So pretty hot. Although just below that, there's a layer called the chromosphere. And I'll put this in a different color just so it's like maybe easier. And this is maybe like 4,400 Kelvin. Right? Maybe as high as 6,000 or so towards the surface of the photosphere. Now the fact that it's so hot in the upper regions here, you're talking about thousands of degrees, and for that reason, basically the entire surface of the sun is a black body radiator. It generates light from heat, right? It's able to excite all of the material at the surface such that it gives off light. Okay? So if we look at the spectra from the sun, and that's like maybe the fifth image, it starts with like red at the top and it goes all the way down to blue at the bottom. And that's actually like a map of all the wavelengths of light. It's expanded. It doesn't just look like one bar. You imagine you took that bar and you stretched it out over multiple lines, and that's basically what you're looking at. And so all of the little missing features, all of the little black bars, those are absorption features from the elements in the atmosphere, the gases in the atmosphere of the sun. Now we've been able to identify something like 70 elements in the sun's atmosphere, and those are basically all of the elements that we can find throughout the solar system, including here on Earth. Those 70 elements. But this also means that there are outer layers to the sun's atmosphere. Otherwise, remember, a black body radiator, like the upper atmospheres of the sun, are going to emit light from every possible wavelength of light, every frequency of light in the visible part of the spectrum and beyond, right? But because there's atmosphere out here in the sun, some of those spectral lines, some of those individual wavelengths and frequencies that excite the gas in the atmosphere of the sun are going to be absorbed and then re-emitted, obviously in random directions. So it looks like, if you're looking directly at the sun, that those emission features that belong to the elements in the sun's atmosphere are going to be subtracted, dimmed out, because they're going to be reabsorbed and re-emitted in random directions, right? And so essentially, and this is not news to us, of course, but if we look at the spectral signature, right, the spectra of the sun, we see a continuous spectrum with the emission lines from the elements that the sun is made of subtracted. We see an absorption spectrum, right? And so we know that the sun's atmosphere is there. We've actually been able to take lots of direct measurements of it, and we can see that the outer atmosphere, the corona, is probably something like close to 1,000,000 degrees Kelvin, or 1,000,000 Kelvin, right? 1,000,000 degrees C, very, very hot. In any case, this region, the chromosphere, um, the temperature climbs from 4,400 to about 6,000 or so Kelvin um, near the edge of the chromosphere as we proceed out into the corona. And we think that there may be magnetism at play there, causing it to funnel all of that heat. But in any case, the absorption lines begin at the chromosphere, right? Actually, I drew this backwards. The chromosphere is on the outside of the photosphere. Out here is the chromosphere. That's something like 4,400 Kelvin on the inside, climbing up to about 6,000 Kelvin on the outside. Now this is where the absorption lines begin, starting with the strongest one, the most common one, and that is the H alpha line. That's a very, very prominent red color that you see in the hydrogen emission spectrum. And it's so predominant that we call the chromosphere because of this distinct red color, mostly from this H alpha line. We also found helium in 1868 from emission from the chromosphere. And that's why we call helium helium, because helios is the old word for the sun, right? And so we gave helium the name for its element from the sun. The outermost layer, of course, is the uppermost, or the upper atmosphere. We call it the corona. And if you've ever seen like a total solar eclipse, it's like this wispy cloud kind of, formation kind of on the outside. It looks maybe kind of like this. The corona. And that's, it extends millions of kilometers from the surface of the sun. You could fit the Earth, inside the corona very easily. It's very, very large. And it's so hot that it can get up to like 1,000,000 Kelvin, probably also from magnetism. But also, the corona is much, much less dense than the rest. It's an atmosphere. Not terribly unlike our own in that it's much more diffuse, it's like gaseous, compared to the rest of the sun that's like much, much more dense, right? The easiest way to see this part, because it's not as bright, because again it's not as dense in material, and so the amount of light that it gives off, while it does give off light, and it's actually pretty bright, it's hard to see it next to the chromosphere and the photosphere, which are much, much more dense and give off a lot more light. Anyway, that's why we call it the corona, right? Like a crown, because it rests kind of on the outside of the head of the sun, so to speak. Now, the atmosphere of the sun is awash with crazy magnetic activity. And we know that it's magnetic activity from our studying of what we call the Zeeman effect. And there are a couple of images in today's bank. I think it's maybe the 10th and 11th ones in today's bank that show that essentially the emission lines that you get will split if they're in the presence of a strong magnetic field. Zeeman effect. Now we already know that the Earth has a very strong magnetic field because there are moving charges, mostly like in the metals and magma and stuff like that, that are below the surface of the Earth. However, we've got a ton of convection currents here near the surface, right? And so if you're talking about a layer of the sun that's, probably deep enough that you could fit whole Earths in it, that are moving tons of material around all the time, you're going to see probably a lot of magnetic activity, right? As if the Zeeman effect wasn't enough evidence of that, obviously we have now a theoretical backing as well. Moving charges make magnetic fields, and if the sun is saturated with these freely moving particles, it should make huge, intense magnetic storms that cover the entire sun, and indeed, that is exactly what we see. All these magnetic fields form loops, essentially, right? Because there's no such thing as a magnetic monopole, right? Magnetic fields always go in loops, like circles, kind of like cyclical currents. Now, sometimes if one of these cyclical currents is like near the surface, it can push away from the sun and kind of loop back toward it, right? So it'll go outward this way and then back toward, and then it'll complete its loop below the surface sometimes. And that can cause material to kind of push itself away from the sun. Now sometimes, if the magnetic field is shaped in just such a certain way, the velocity of these particles will just kind of be so perpendicular to the surface that material just kind of gets ejected. We call a structure where this kind of thing can happen on the surface, we call it a coronal hole, like a hole in the corona, right? And especially if, it's the corona that's doing the ejecting. And we call this flux of particles that comes out of the surface of the sun, from the corona, we call that the solar wind. And the solar wind extends about 100 AUs from the sun, kind of out past the edge of the Kuiper belt, to where it finally can't push dust or ices and gas particles and things like that anymore. There are dark spots on the surface of the sun, and Galileo is one of the first to sort of popularize that these were around, but there's evidence that the Chinese found them thousands and thousands of years ago. We call these sunspots, and they're not really that dark. They're only actually slightly darker than the surface of the sun. But it just so happens that because they're just a little bit darker than the sun, which is super bright, they're kind of easy to see by comparison, right? Now, once upon a time, they used to think that these sunspots, and this is like if you took one of these and blew it up, right, to try to show a close-up, these sunspots are kind of darker in the middle and not as dark on the outside. And it's for that reason they called the middle the umbra and the outside a penumbra, because they thought this was a shadow for something. I think it was Galileo's doing, likely. But Galileo, while he may have thought incorrectly that this was a shadow, he also thought correctly that he could track the progress of these moving things to figure out how long it takes for the sun to rotate. And he was right. The sun rotates in about 25 days. But because we're actually also moving around the sun in our own orbit, it looks like it takes about 27. So it's a 25-day sidereal period and a 27-day synodic period, because we're also moving around the sun. But also, very much like the gas giants, because the sun is just a big ball of gas, it also rotates more quickly at its equator than it does at its poles. It rotates differentially, just like any other body that's made out of gas. These sunspots, these cool spots, which are caused by crazy magnetic storms on the surface of the Earth, some of which look like big giant loops, right? Um, we call those prominences, right, when they loop back and are anchored to the sun. We call them solar flares when they eject material. But these prominences and flares, these magnetic storms, these strong surface features, these sunspots, generally only live about 10 days. Some of them can live longer, sometimes, as much as 20 or so, but generally they live on the average about 10 days. And it just so happens that if you wanted to track the appearance and the disappearance, how long they live, how far they go, where they appear on the surface of the sun, they follow a pattern. And if you look at, I want to say the 15th and 16th, maybe, images in our image bank for the day, you'll see that they start kind of out here. And there are fewer of them, and then eventually there are more and more and more, and they gravitate towards the middle, right? The longer it goes, the more of them there are, and the more they come closer to the equator. And in so doing, they make this kind of, over the course of time, they make a pattern they call the butterfly, right? We call that a butterfly diagram. If we map out the positions, the latitude positions of these sunspots over the course of time, we'll notice that they start out there and then they kind of taper towards the middle and make like a butterfly. But every 11 years, it starts over. And the reason for that is that there's tons of magnetic activity, right? And so there's this tremendous magnetic field that the sun has. But the magnetic field lines don't stay constant because the sun is moving more quickly at its equator than at its poles. And so the magnetic field lines wrap around tighter and tighter and tighter until eventually it snaps and reverses every 11 years. Kind of like what happens to the Earth's magnetic field, except the Earth's magnetic field takes something like 450,000 years on average for it to snap and reverse, right? This is every 11 years. During the 16 and 1700s, there was a minimum of solar activity called the Maunder minimum, where there were fewer of these sunspots than kind of on the average. Now there are two images. I want to say those are of the 18th and 19th maybe? Or the 19th and the 20th? But they're images of the same place on this Earth. If you look at the first one, you'll see it looks like, obviously this is from the 1600s to the 1700s, so there's still like horse-drawn carriages and people living in tents and all this and that, right? Stone stairs, blah blah blah. People wearing older-looking clothes. And all of this, everything in this image is on a river. And that is on the river that is in the second image. Now, there are a couple, or maybe a few dead giveaways, right? Obviously, in the very far left of this image is Big Ben. And that means it's attached to the Parliament building, and then across the river Thames, is the London Eye, which is this huge, it's like a Ferris wheel, except it moves really slow. It's a tourist attraction. It allows you to have like a panoramic view of all of London. And you have to pay, I forget how much. Last time I was in that was like early 2000s. But you pay a few pounds and you get to go around this loop-de-loop-dealy and get a good view of London. So yeah, this is London. So during this time, normally the River Thames doesn't freeze over all the way in winter. But during the Maunder Minimum, during the 16 and 1700s, the River Thames stayed completely frozen basically the entire time, for years and years. People lived out their entire lives, lived and died on this river, and it was frozen solid. So what does that mean for us? Well, that means that sunspots, solar activity, right, adds to the amount of heat that we experience here on the surface of the Earth. Does that make sense? Well, yeah, if you have a prominence, it may loop, but if there's solar flares from these sunspots, then they're going to eject hot, charged material out into space. And anything that they come across, obviously, is going to make things warmer. So, sunspots actually have an effect on life here on Earth. And that's why even nowadays you can check out the solar advisory to see what kind of radiation exposure you're going to get if you get on an airplane. In any case, when these hot charged particles reach the surface of the Earth, they do kind of a funny thing. And some of the later images in today's bank will remind you of Maxwell's equations and this funny thing we call the Lorentz force law. And I'm just kind of going to give you the short version. If there's a particle, a charged particle, in an electric field or a magnetic field, right? An electric field will put a force on a charged particle, just like if you have two charged particles near each other, if they're like signs, they'll repel, or if they're opposite signs, they'll attract each other, right? Because one charges in the electric field of the other and vice versa, so there'll be a force. But similarly, also, if a charged particle is in a magnetic field and it's moving, or if there's like a current, right, moving charges, then the magnetic field will apply a force to that moving electric charge. And that goes according to the right-hand rule. So if there's a charged particle moving this way along my index finger, and it's in a magnetic field that's oriented this way, straight up and down like my middle finger, then my thumb will indicate the direction of the force that this charged particle is going to feel in this magnetic field. Now, if this charged particle just so happens to go up near a magnetic field line, right, then it may swirl around it and you get this funny kind of accelerated radiation that is responsible for the aurora borealis and the aurora australis. And that's the last image in today's bank. It's pretty neat, right? I don't know if I'm supposed to be telling you about this, but the one time that I saw the aurora borealis, it was same trip actually that I saw the London Eye in London, but I also went up to Scotland because I'm actually a wee bit Scottish. And so I went up to Loch Ness, and I walked all the way south along the loch to this restaurant where I had dinner, and I was walking back to the Loch Ness Youth Hostel after playing fetch with Nessie, who was actually somebody's dog named Jessie, so I'm pretty sure it wasn't the actual Loch Ness monster. But as I was walking back, I was walking on the road by the loch, and it's kind of high compared to the water, right? And if there's no wind, water is like a mirror, right? Loch Ness, because, it's a locked lake, right? There's no inlet or outlet or whatever, so it doesn't flow. It's still like glass for miles, or kilometers, I guess I should say. So that night, when I saw the aurora borealis above me, I also saw it reflected in the water below me. That was maybe one of the coolest things I ever saw. So if you ever get the chance, I highly recommend that you go and try to see the aurora borealis at least once in this life. It's worth looking at. Okay, that concludes our Chapter 11 lecture on the sun and how it works. If you have questions on today's material, please get a hold of me through the normal channels. And I hope you have enjoyed this lecture as much as I have enjoyed giving it. I'll see you next time.